Okay, we want to look at our current best understanding of the essentially the electron configuration for atoms in solids, right? We've looked at so far isolated atoms, just an atom in the gas phase all on its own, and we had the Bohr model, the wave mechanical model. But what we need to do now is think about what happens when the atoms come together. The electrons start to interact, and well, in fact, what happens is the energy levels in the isolated atoms come together and they would appear to be the same, but the Pauli exclusion principle tells us that they can't be. And what we observe happening is that then they spread out a little bit to different states, and that depends on the number of atoms. So if you get a mole of atoms together, a huge number of atoms, you get all these different states. And that's the basis for the band structure or the band theory of solids. Okay. Now, a few things that confused me when I was learning this is, first of all, and it sounds silly perhaps, but why on earth do we call it the band structure? Why is this what's the band? And so I'd like to try to address that with you and show you as well how it's such a useful model. So what I wanted to do is discuss a little bit here an isolated gas atom, as we've seen before. So I just put n equals 1, n equals 2, and I'm going to use that as the beginning of a conversation here that we can have, where I'm going to plot the electron energy, okay, the electron energy, or the energy of the electron, versus I'm going to do versus the number of atoms. Okay, and that way we can actually start with one atom, which is what we've seen over here for an isolated atom. And we've done that before. This is an isolated, poor little isolated atom, all alone, right? And then, well, what's going to happen when we get 2, when we get 3, when we get 4, and so on, and when we get all the way out to a mole, 10 to the 23. And of course, that's going to be kind of broken axis there. All right, great. So, let's just take a general electron energy level, some energy level. Maybe it's 3s or who knows what, but there it is. And we've defined that previously in our discussion of electron configuration. But now what happens? We need to consider when we get 2 atoms coming, atomically close together, and to avoid having exactly the same energy levels, they separate out so that they're not so-called degenerate. And then if we got 3 atoms, we get 3. If n equals the number of atoms here equals 4, you have 4 different states, and so on. You go all the way out here, and you're going to see me draw 10 to the 23. They spread out a little bit, 10 to the 23 different states. And of course, I'm not actually going to do that because I want to keep this video short. But what happens? Look at this. I've drawn in here now, I don't know, maybe 50 lines or something like that. Well, they all seem to overlap, and they seem to become effectively continuous. Okay, so we've got this effectively continuous range of energy levels. Okay, and that is in fact the basis for this band structure. We got all these levels, and what are you going to call that? Well, you could call it a solid range of values. You could call it a stripe. So maybe if I had described this model years ago, I would have called it the stripe model of bonding in solids. But the name that was used is band. They thought that range of close energy levels that are so close that they're effectively continuous looked like a band. And I can kind of see that, but as a student I struggled with that. Anyway, I hope you can get past that. And this is where the word band comes from, and it reminds you that we've got this effectively continuous set of energy levels, really, really tightly spaced. Now, we can do more with it, of course. And so what I'd like to do now is show you another way that you'll sometimes see this described. And again, we're going to plot the energy of the electron here, the electron energy. But this time, why don't we actually plot versus distance, versus interatomic spacing. Okay, we've seen that before, R. And so we know what we're going to be interested in is when R equals R naught, which I'll remind you is the equilibrium interatomic spacing. All right, equilibrium interatomic spacing. So there it is. So what's going to happen then when we go from infinite spacing to R0, which is the spacing between atoms in a solid? That's what we're after. This is solid state chemistry, so that's what we're trying to figure out. So let me give myself just a little bit of space here. And, well, why don't we start with what we should probably be comfortable with, and that would be at infinite separation. Well, at infinite separation, that's nothing more than this lonely atom that we've discussed, this isolated atom we've discussed before. So there would be one energy level. And it's kind of like going the opposite direction from what I showed you before. What happens is as you approach, well, as the atoms approach one another, we see these energy levels separating out. They separate out into, again, a range of values. And then, so then the question becomes, all right, how can we use this to explain things like conductivity or the optical behavior of material? And again, I'll remind you, I give you this analogy of the Bohr model. And what we discussed with the Bohr model was, say you had an electron here in n equals 1, and you wanted to promote it to n equals 2. Well, we said you'd have to have enough energy to cause that excitation. If it only had enough energy to get you to n equals 1.5, for example, then we know that doesn't happen. Energy is quantized. So similarly over here, say we had all these energy states here occupied with atoms. So for example, if this was from 3s and there was actually 2 electrons in it, we could expect to see there's only 2 states available, and so each of them is full. So all these states here in this band that you've got at r equals r0, right? Go through here. That's your band. They're all full. All the energy states are occupied, and this is technically at absolute zero, right? There's no thermal excitation. They're just all sitting there at their lowest energy, just like we just saw in the isolated atom. The electron would drop back down to its unexcited state, its ground state. So these are all the electrons in their ground state, just this time in a solid. Now what we need to think about is, well, what happens if we want to promote it up? So let's just say that there was another, the next energy level up, and I want to just keep this actually generic at this point, so I'm going to erase 3s there. Okay, so just whatever the next electron energy level is that you had in the isolated atom, well, that will also spread out as the atoms get close to one another. And what you might find happening is this, that the next set of possible energy levels is separated by a little gap, a little space here, right? That's the little, it's like the space between n equals 1 and n equals 2, for example. It's not allowed. The electron cannot exist there. And it's a if you draw this as a band, I'll show you the way that these band structures are sometimes drawn. If I were to draw that effectively just in one dimension, what we often do is we just go like this, and we'll draw a little kind of a rectangle like this. And I could even color code it just for kicks. And so there's your lower energy states. And in this case, if they're occupied by atoms, we're going to call that the valence band. Alright, and actually my color convention, I'm going to get loose with that. Should have been in my new terminology color. They're orange. And then we've got this next set of energy levels that are available but unpopulated. And what happens when you give the electron enough energy to go up? It's free. It moves away from the nucleus, and it's free to conduct. It's free to conduct. And so we actually call this the conduction band. But what might happen, as you can see in this example we've done here, is there's this gap in the bands. You can go from, electrons can move in here. These are allowable values. But to go above that stop green line, they'd have to jump across these values that are not allowed. They're not permitted. And so that is called, it's a gap in the band structure. It's called a band gap. Okay? A band gap. And We can use this to describe the behavior of materials in terms of their electrical properties. And we can explain optical properties and stuff as well. And you'll notice that there's going to be some structures that can have a band structure that looks like this, where we've got a valence band and a conduction band, but no band gap. And that would be the situation where, say, what happened is this these blue energy states actually separated out more than I had indicated. Right? So they spread out even more, such that they overlapped. And this can happen, and they overlap. Well, now if they overlap, you're going to have no band gap. And what does that mean? Well, that's fantastic. That means even just at room temperature, say for example, there's enough thermal energy to excite an electron up into the conduction band to free it up from the nucleus it was originally bound to and allow it to conduct electricity. So metals, for example, have that type of band structure with no band gap. And then what we can look at are some semiconductors. And so semiconductors will have a band gap, and insulators have a band gap. And the criterion between the two is fairly straightforward. It's the size of the band gap. If the band gap is, and we're going to draw a line in the sand here of 4 electron volts, but I'll just mention to you that if you look at other sources, you might see as small as 2 electron volts. You might see up to about 4 electron volts. The gist of it is, if it's a small band gap, relatively small, in fact often things that could be crossed by a photon, 2 to 3 electron volt range, it'll be called a semiconductor. In this case, we're going to just pick a convention, so we'll use 4 electron volts. If it's greater than 4 electron volts, it's really difficult to free an electron up, and that is then called an insulator. Okay, and if the band gap is less than 4 electron volts, well, it conducts part of the time, so we call it a semiconductor. Alright, so that's the band theory of solids in a nutshell. I hope that was useful. Thanks.